Thank you, Avinit, and thank you, Nesli. It's my pleasure to be the first speaker of this morning, and it's a nice morning that I could meet all of our structural steel giants, and I'd hope we'll have a good full day session on sharing the full thoughts of our experience as well as how to grow forward. So before presenting this mega structures and use of structural steel and its challenges, I just want to take a case study apart from our thoughts to share up. For L&T, we are guided by our AM Naik, and as you know, it's 55,000 strong employees. Just to share a slide on that. And that's our business. We do the factories and buildings. We have heavy civil infra. We have transportation, water, renewable energies, metallurgical, heavy engineering, machine. So these mega structures, we have airports, tall buildings with large footprints. These would require to have large spans. In such a case, you require to go for a structural steel to reduce the tonnage and also optimize on the foundations. So basically, we go for less weight and more strength concept. And also we go for maximum column free space, wherein architects can enjoy in planning their own themes, which will be more or less agreeable to the clients. It also gives an architectural freedom to carve out their imaginary and articulations. And I would like to develop on a couple of projects apart from Mumbai Airport. Bangalore Airport also done by us, which has got a crazy shape of flowing elements, which is possible only in the structural steel. If you do concrete, it will be almost 1.5 times the cost what you have done. So importance of that is to achieve the architectural intent and also go for a lightweight and large span structures. This is the view. Just to go for that building. This is a plan and isometric view of our model, which has got 2 piers, and on the north side, which is the head house roof. So you can see this. This is the head house roof we call. Most of the points of discussion would be on the head house roof because it's an 18,000 ton structural steel with normal CHS, RHS sections only. So we have this head house roof which is equal to 10 football grounds of area, spanning 34 meter by 64 meters. It is supported by 30 mega columns, which is of each of 2.7 meter dia. This building does not have any connection to the terminal itself. To have a glance on the plan, we have, this is the shape of that, this being the north for that, 2 piers and 2 more piers on this, and main processor building here. We have separated all with expansion joints, and this area comes to the head house roof in this top portion, which is the basic departure check-ins. So the features of that is this is single largest roof without expansion joints in Asia, and we have incorporated all the temperature control, outside being ambient of going up to 10 and inside 24, and also outside being 40 and inside 24. We are designed to facilitate modular erection. All the trusses what we produce, which I'll go in detail further, which will have modular erection with a constant spans and a concept called pods. Some of my friends are here who are also associated in this process of design. A framing plan is a rigid diaphragm action which is connected by top and bottom cards, and the redundancy of cantilevers we have, which means actually when we connect all the 30 columns, we have cross trusses which will mutually support each other. We could achieve up to 35 meter cantilevers as per the architectural intent. Also, it has got a 1 kilometer periphery along the total head house roof perimeter, which is this portion of it. And you can see around 34 skylights, which are 34 meter by 34 meters with a rise of 6.8 meters.
So as I was saying, 30 numbers of mega columns are there, it's a 2.7 meter diameter, and what you get is clear space of 64 meter by 34 meters. And trusses are as at maximum as 47 meter because diagonal of 34 and 64 in the mutual. We have a connection of RCC building at level 2. Basically, it could give an advantage for the structural system of the main terminal building. We have 2.7 meter diameter columns and has got a pile foundation of 2.4 meter thickness, which is 1.1 meter diameter piles for 24 numbers. So all this we could work out with the PM curves from the basics itself because we don't have any references to be taken, and all we have done is a deformation based analysis. So there was some of connection. We used to have around 24 joint connections at a place. When you have trusses meeting at one location, we could not develop the plates. We have to use the members itself for the connection of 40 thick plates for the connections. Like we have this one wind is very critical in this. We have 120 psi force for that, and roof structure has to be tested in FM laboratory for taking care of this wind uplift. In the corners, we used to get 3.5 and 5.8 because when the perimeter goes, though we try to make it smoother, if we see this wind model, though we try to make it smoother on the edges with the curvature, still we have a corner effect which gives us around 5.87 kilopascals of the wind pressure. We have used high strength friction grips, the bolts for the connection of all the major nodes. We don't want to have any chances, and we can't weld it. Majority of the trusses, when they brought it from the shop, they are all welded, and the connections at the site are being bolted. So we have designed for all the 6-member forces for that, which includes the torsion for that. And also major butt welds are tested for RT. We had difficulties in testing the RT at some of the locations, but then we have insisted on to get a quality for that because this is a crucial junction or is a crucial roof for us. This erection is a challenge for us because some of us may be knowing we have important Shivaji statue in the middle of our total head house roof. So we could not construct the building itself in the middle, but due to the lapse of the time, we need to proceed for the construction and erection of the trusses, which left us with no option but to manage peripheral cantilevers alone with the central 2 base columns and central void to Shivaji statue. So we have used erection by of a unique scheme. I'll explain the scheme itself here without using the floor slabs. We use the skyway trusses. So just coming to the analysis and design, so that's the model. So we have done the combination of roof with the head house for the floating columns as well as connection with the floor at the second floor. So over 1200 concrete piles reduced from original assessment because this is for a concrete saving. The steel structure which we had for head house roof could have more impact on saving of the concrete as well because we could use the stiffness of the steel structure to our concrete, which is a base structure on the terminal. So this is the cross section how we have done. So this explains. This is the basement where we have underground structures which is 4.4 to 5 meter depth for all the MEP rooms and sumps. We have this as the arrival corridors, and this is the arrival plaza, this is the arrival corridor, both different levels. And we have third level for all the services there, and this is the departures area where we have got 15 meters height. So some of our friends was asking whether it is a fireproof painted or not. As you know, it is 20 feet higher than that. NFPA doesn't require for this type of structures. Without a fireproofing, it's fine. So these locations, we have 15 meters height, and all these are encased concrete columns. So you don't require a fireproof painting in this. So this is a description of the base pile foundations. We have used different diameters, maximum being 1.2 meters in the mega columns, and that's the plan. So we have 340 meter by 267 meters, amounting to 1 kilometers perimeter, 1 kilometer perimeter with 34 by 64 meters. All these spots are connected by the trusses, which we call a main truss and secondary truss. So if you see what I was saying earlier about the mutual supporting of trusses, so this is the Mayo column, sorry, can't see. This is the Mayo column and the pod around that, and the diagonal trusses and the straight trusses will join to support mutually each other. So though span is 34 by 64, effectively you'll get only 47 meters span, which is the idea of introducing the pods at a level at distances of 34 meters. So these are the pods I was speaking. So first we done a trial on this pod for erection of it without any lateral support for one span being the trusses erected. Then we tested for the wind and then erected the cantilevers. As I was saying, this is the area where Shivaji's statue was there in this. So we had a huge issues on the cantilevers because deflections, since the central supporting connection mechanism is not there. So this is the model for that, and that's a span of 34 by 64 meters with a purlins of 2.83 meters. We have a build-up of almost 280 mm for insulation purpose apart from the membrane roof, which is a TPO, largest installation in India. It's 1.4 square meters, 1.4 lakh square meters, sorry. So this is the model which we can see this. This is the span of the truss, which is 34 meters, and diagonal, 47 meters there. And we have a pod connecting here, and this overhangs there. All these cantilevers are overhang cantilevers. So we have a strength, but at some of the locations we have a cross trusses, which will also mutually support the end points of the cantilevers. So we could get the deflections. I'll come to the deflection, which is a critical point of 35 meter span cantilevers. So this is a Mayo column cross section, which is a 2.7 meter diameter with a built-in sections of 50 mm thick plates to 16 thick plate combinations. Main plates being 50 thick plates. It has got a tapered section which is ranging from 35 meters to balance 47, 12 meters here up. So this is the cross section which goes through all along. So we're done through the P&M calculations for this. We generated the curves and we have achieved all an optimal steel design there. So this is the detailing. I don't know, is it clear, the black or? So these are the holes for doing concreting, because we have a steel plates coming at every 2 meter regular intervals. First we erected the structural steel members, means all the plates in position after welding and connecting it up. Then we had at 2 meters the structural steel plates with the stiffness, and then we did the concreting for that through these holes at every 4 meter lift. So what are the challenges there? We have the constraint on access for the whole roof at a time, because this, as it is a brownfield airport, we don't have any access of full airport terminal at one point of a time. When we started working from 2007, we could get 50% of it by 2009. So you can understand the logistics part of it. And we have multiple sources of material coming from Singapore, coming from China, coming from India. So this logistics did not give us a lead of getting all the material at the same time or to plan it. So a huge problem of logistics for us. Anyway, one more important design aspect is the lack of fit. Once we start fabricate and get it onto the site, we found it is not meeting the requirement, because we have some alignment deflections of the Mayo columns, which is off by 50 to 60 mm. Some locations 150 mm shifting. So what do? We can't de-erect the truss there. So we have to give additional plates and do the welding and then bolt it again. So these are all the lack of it is an important aspect which may have to play a role in during the site installations. Front of erection at the brownfield airport, I was discussing that already. Cantilevers of 8 meters, 35 meters. Here we have deflections on the 8 meters cantilever up to 180 mm in the initial installation stages, just because we don't have the central Shivaji statue area covered with a clear back spans. And also we have 35 meters cantilevers which has got a allowance of 495 mm deflection. As you know, it's an architecturally covered building, and all this total structure is totally covered by GFRC element, glass fiber reinforced concrete, and inside it is glass fiber reinforced gypsum. So though you don't see the structural steel, it's a huge effort for all the engineers working there to produce a deflection which is less than 495 mm. We used to get almost 895 mm. So architect needs to discuss, and we had a discussions with GFRC vendors or suppliers who are kind enough to modify the supporting system to achieve the architectural relevance of 150 mm. So we could achieve that, which is the result of what we see now. So these are the modules. I'm just showing the plan so that when I go to the one erection scheme, you can understand it better. This is the view, which is the planned erection scheme. It's a link problem. The GISPL on this, it's a complete erection module. So we have erected a temporary TARS on one of the left corners, and we have made a connected cable between the columns, and then we have launched a 650 kgs girder there, each of the 2.5 meter length, 650 kgs, and skyway truss of 1.25 ton per meter. We launched it, and that is going for all the 34 meter spans. We chose 34 meter span as the direction for us to launch this pod. I'm going to show you the pod erection methodology. Pod is a thing which is 34 meter by 34 meter, which is taken on top of the total trusses to install on top of each of the mega columns. So this is the skyway truss which is being installed there, which was installed at the time, and this was to ensure there is no moment transfer onto the column. So these are all pin connection there, and we have developed the trolleys, which we call bogie, to transport all the pods. Then we have taken all the trusses which will form the pod and erected the columns on top of the temporary truss, temporary base which we have provided. Erected the columns, then taken up with the mobile cranes, erected the trusses. So if you see you can see that on the left corner bottom, the pod is being formed. Each pod weighs around 250 tons. So this is being shifted on a span of 34 meters, and it took almost 12 hours to shift for 80 meters length. It's almost 1.5 meters per minute. So this was transported all along for all the 30 columns by this way of skyway truss. So each of the thing almost took 9 months for that erection itself. Because these 260 tons, it cannot be carried out by the structural slab which is below, and we cannot use the slab for erection purposes. So it has to be done by putting an additional truss, which is this model. So each of the trusses are transported, and we have a deflection allowance of the maximum 34 meters with a 92 mm. And one fine morning, for the first day of the installation of a pod, there was a complaint from the airlines. This is reflecting too much. Then we said we can't paint it now because anyway it's being covered by the roof, so we can't paint it now, so keep it without a paint there. So we do the painting there, but we have done all first coat of paint, balance being second coat on the top. So these are the pods being installed on the north side as you go on. That goes. Last one being the cantilevers. So this is the cross section of the pod where we erected it. We have put a walkway truss, and this middle one, this one is the bogie we call. This is the bogie because this transports this total skylight, and after going to the location of column, it lowers that. So this is the truss walkway for feeding that, and feeding material can be taken to the walkway in between. So that is a cable which is connected for initial truss launching. So this is the launching scheme for the cable and the launcher, which we are seeing in the initial time. So these are strand jacks of 25 tons winches we used, and we have had orthogonal trusses of 23 tons and a maximum of 47 meter spans. Maximum truss weighing for 36 tons. Only the pod is a big one, which is at 250 tons. Balance all, it's fine. So we have at one point of time we have put 220, 285 ton cranes for erection of these all materials at successive times. Just coming back to the presentation part. So I just had a small video which will just capture what is done at the time. There is no audio here, so fine. So this is a video for movement of that. You can see how this is going, and you have a hydraulic jacks, the pistons which will move that much, that's all. So every piston movement it will go for 4 meters distance. So we need to wait for long to get it. Just a glimpse of what it was done at the time. And there are erection images which has got a walkway truss on the bottom here, and the pod which is moving onto the other side. You can see the jack. This is the location, so this is the position when all the pods are erected in 2011. So it is around 2.5 tons times the steel of Eiffel Tower. Presumably 7,000 tons is the Eiffel Tower there. After erecting all the cantilevers, this is the view it gets. So important thing I was trying to explain was, this area was the cantilever, which is 35 meters, and the deflections going up to 895. We had to support the total truss and unbolt the mega column, and then cut the members, re-erect it and weld it at some locations because the deflection was so high. It's a huge risky affair, but we had to do it to control the deflections within the architectural limits. That's the steel what we used. Once we done that, we had a framing on the mega columns which will come to the architectural front. So all the GFRC panels being erected there, and that comes the cantilever. So the importance of that is structural steel erection and the design, though it's complicated for that 20,000 tons of steel, with the support of all our designers and also the suppliers who made a huge change in that, we had an opportunity to do this lifetime structure of Mumbai International Airport T2. Thank you.